Good evening. Welcome to the April meeting for Silicon Valley ACM SIGGRAPH. I would like to thank the Bay Area ACM chapter and the Los Angeles ACM SIGGRAPH chapter for their help in co-sponsoring tonight's meeting. Tonight, we will have a presentation by Matthew Chan talking about AI work at NVIDIA in creating 3D models from 2D images. I am Alex Junkirk, Chair of Silicon Valley ACM SIGGRAPH. Joining us tonight is Bill Bruns from Bay Area ACM, and also Joan Collins from the Los Angeles ACM SIGGRAPH chapter. Before we get to tonight's presentation, we would like to tell you about our organizations. Silicon Valley SIGGRAPH typically meets in various Silicon Valley companies about once a month. Our meetings are great for networking and for learning the latest technologies. Since COVID hit, we have been online. However, we hope to get back to in-person meetings eventually. Now let me introduce you to the officers of our chapter. I am Alex Junkirk. I am the chair of the chapter. Brent Simon is vice chair. Carl Anderson is treasurer. And Ken Trukowski is a member at large. Finally, this could be you. We are always looking for more volunteers and need help in many of the chapter activities. In particular, one of the ways where we could use a lot of help right now is finding venues for in-person meetings. If you like what you see here, please consider joining us. You can find the latest information on our chapter on our website or on our meetup. You can also contact us using this email. We also have a YouTube channel where many of our events are recorded. If you're watching this on YouTube, these links will be in the comments. Otherwise, you can find this information later by typing Silicon Valley SIGGRAPH into Google. One of the main events for people working in the computer graphics industry is the annual SIGGRAPH conference. This year, the conference will be held in Denver during the last week in July. It's a great way to get immersed. It delays the computer graphics for a whole week. Registration for the conference is now open, and early registration will continue until May 14th. These prices will be lower than what will be available later. Please find out more information on our meetup or at SIGGRAPH.org. I'd now like to invite Bill Bruns to tell you about Bay Area ACM. Take it away, Bill.
Thank you. The SF Bay ACM has been in the Bay Area since the 1950s in different forms. We cover all software topics. We have both a YouTube channel with hundreds of videos from past meetings and a meetup page with over 12,000 members. You can find these things by searching for SF Bay ACM. We strive to have 2 meetings per month, one generally on AI and machine learning, and the other on general computing topics. We've had topics on A/B testing, on programming Android, earthquake detection, various things. Our next meeting, as you can see on the slide on the screen, is more about AI or machine learning, tutorial on RAG, and you can join that either online through Zoom or YouTube or in person at Hacker Dojo in Mountain View. Hope to see you there. Thanks.
Okay, thank you, Bill. Now I would like to invite Joan Collins to tell you about Los Angeles ACM SIGGRAPH chapter. Go ahead, Joan.
All right. Thank you very much. I am Joan Collins, chair of the Los Angeles ACM SIGGRAPH. And thank you, Lesh and Bill, for arranging this 3-chapter event this evening. The other LA SIGGRAPH officers in Los Angeles include Vice Chair Larry Rosenthal, who produced this event coming up on the Metaverse, and Secretary Rick Hernandez, Treasurer Dave Kurlander, membership Sharon Eisenberg, and volunteers Franz Antonella Benjamin. Our meetings coming up include what you see on screen, the May 14th Metaverse 2024, Can Web 3D finally provide a path to the metaverse visions? We're hoping June, we have the 4th of 4 annual art show. It is a month-long exhibition with over 20 artists in it. September coming up, we also have an outdoor multimedia show for a very large audience. That event's called Open Sky. We're very active chapter. We hope you join one of these chapters here tonight. And back to you, Lesh.
Okay, thank you, Joan. And now to introduce tonight's speaker, here's Ken. Okay, go ahead, Ken.
Thank you, Alesh. Tonight's speaker will be talking about the technology behind the 3D video conferencing at last year's SIGGRAPH Emerging Technologies and last month at the GPU Technology Conference. Matthew joined NVIDIA as a research engineer in 2022. They primarily work at the intersection between graphics and generative models, specifically how they relate to 3D scene synthesis, reconstruction, and understanding. They graduated from the University of Maryland, College Park in 2021 with a bachelor's degree in mathematics and computer science. If you could, please hold off your questions until the end or type them into the Q&A and they will be addressed at the end of the talk. Thank you. Matthew, take it away.
Okay, please welcome Matthew Chen.
Thank you for that wonderful introduction. Great. Well, hey everyone. Thanks for stopping by. As they mentioned, I am Matthew. I'm from NVIDIA Research. Today I'm going to be presenting a little bit about how NVIDIA approaches the problem of learning photorealistic 3D people using in the wild data. So what that means is that we're going to actually leverage AI and we're going to use that to create high quality, robust, and efficient digital humans, all from easily capturable and also widely available data online. I am on the very tail end of recovering from a little bit of sickness, so you'll have to forgive me if I'm frequently reaching for my water bottle here. Otherwise, let's go ahead and jump right in. So the first question that we should ask is, why do we even care? Why do we want to do this in the first place? So there's a good number of applications for 3D digital humans, but I think the most obvious among them that we have here is telepresence. So in the most literal sense of the word, telepresence is the ability to allow people to be digitally present, even at potentially extreme distances. So this is not really a new problem, like at all. It's actually quite old. So a lot of the efforts that we see date back as far as the early 2000s and a little bit further. And there's a whole bunch of notable attempts at this problem. I'll show a few here. Way back, we found out that even something as simple as placing people in a physically accurate world with, a TV monitor and a digital reproduction of half a table through the screen can help a lot with realism and feeling present. More recently, if we skip forward about 20 years here, in 2021, we saw Meta attempted to solve this problem through the use of codec avatars with their headsets. Recently, also, that same year, Google attempted to solve the same problem without headsets. So they introduced Project Starline here. Similar idea, 3D telepresence of people, but without a head-mounted display. Even more recently, so that is last year, Apple, this is something that a lot of you probably have seen. Apple produced the persona avatars for FaceTime and other applications using the Apple Vision Pro. So all of these approaches that I've just covered really have excellent quality. The thing that they all have in common, though, is that they're trying to reproduce reality as we see it. And we wanted to know at NVIDIA, what happens when we choose to stray from this assumption? So is it possible to bend reality for a little bit better communications? Let's see. What if instead of reproducing reality, we could do this? Do I have audio?
Yes, I can hear you.
Fabulous. So there's a lot of stuff going on here. If you look in the bottom left corner, we have stylization. In the bottom right corner, I'll play that one more time. We have translation. There's some eye contact. And a lot of this, if you caught that in the top left corner, or I suppose the top right corner, is all coming from a single 2D input. This is just a sneak peek at what I'm going to be covering today. But before I get to exactly what it is that we're doing, before I give you too much more information, I'm going to go and take a little detour into how we do this. And then at the end, we'll really get to why we want to do it this way. So to start off with, it really all begins with generative models. Cool. So let's start with GANs, GANs, which stands for Generative Adversarial Networks. GANs are relatively new. They're only about a decade old as of today, and they've progressed truly extraordinarily fast. So since the very first GANs that we saw in 2014, it's taken less than 5 years until we were able to produce humans and faces that were indistinguishable from the real ones. To prove that, actually, I have this study here, which showed that a collection of curated images is indistinguishable from real images for the average population here. And we've seen even more of this in recent years. Cool. So I'm going to go do a little bit of a deep dive into what's actually going on under the hood here and how these things work so that we can get a better idea as to what we're doing in the end and why we care. So what is the goal of a GAN here? It's actually a really simple goal. We want to train a model that converts from random numbers into random people. In this case, we're converting into images of random people that don't exist. These images should ideally look real, but also ideally not necessarily be real. Let's do a deep dive into how these models are trained. In the case of GANs, there's actually two networks. We have a generator on the left side, and we have a discriminator on the right side. So the task of the generator is to generate images from these random noises, the latents all the way on the left. And the task of the discriminator is to tell the generator how good or how bad the generated images are, and then also tell the generator how it can improve to make the images look more real. So in recent years, NVIDIA has actually proposed a series of StyleGAN papers, each achieving state-of-the-art in image synthesis at the time of release. So on this screen here, I have generated images of StyleGAN 2 on the left and StyleGAN 3, which is the newer variant, on the right. In StyleGAN 2, you notice there's a handful of artifacts, stuff like sticking. If you look closely at the beard here, I'm not sure how smooth it comes across on a Zoom call. But you may see there's a little bit of sticking along the beard as if the fine details are glued to the camera lens. Whereas on the right, it looks a lot better, but you'll notice that even as they move the camera around, the person changes a little bit. And that's not really what we want. Because while this looks really good in 2D, it's actually just a 2D image of a person. It's not really a 3D object. And while 2D is nice and all, 3D would be better. So one area that we've actually seen a lot of advancement in the last few years is the use of GANs, so these same architectures or slight modifications, to instead of creating 2D images, we can create 3D objects and scenes. I'm going to call these 3D GANs or 3D aware GANs. So 2 years ago, we presented the 3D aware image generator called EG3D. And just like the 2D GANs, 3D GAN models are trained using unstructured images of 2D people. So you see that in the bottom left. And then yet, despite never really seeing 3D people or multi-view images or any other even inherently 3D information, these networks are able to generate multi-view consistent images and videos and also objects, all in real time. So what we really strived to answer here was the question, given the identical collection of images and data that we used to train the previous 2D GANs, instead of creating photorealistic 2D images of people that don't exist, can we create photorealistic 3D representations of people that don't exist? Unsurprisingly, because I'm here today, yeah, we can. Oh, I missed a few slides. Let's skip these. So how do we train this 3D GAN? Let's go back to the basics here. Starting with a 2D GAN, the generator inputs a random noise vector, and then it's going to use that to create a 2D image. The discriminator on the right-hand side then observes that 2D image and provides feedback on the realism and what parts should be modified to improve the realism. For a 3D GAN, it's quite similar. You have your random noise on the left side, you have a generator, but instead of creating a 2D image, it creates a 3D object. Now, we then randomly sample a set of camera parameters from a distribution of cameras in some real-world data set, and we're going to just take the camera and we're going to render out a 2D image. Then we're going to take that same 2D image and we're going to feed that to the standard 2D image discriminator. So what that means is that these 3D GANs, despite operating in 3D, can use identical discriminators and data that we use to train the 2D GANs with no modifications. To recap, 2D GANs and 3D GANs are very similar in architecture. The primary difference between 2D GANs and 3D GANs is simply that the generator creates a 3D representation and then differentiably renders it to a 2D image before passing the result to a standard 2D image discriminator. An important note that I touched on in the last few slides is that we train entirely from 2D in the wild images rather than ground truth 3D data. So just like the previous 2D GANs, 3D GANs train from these in the wild 2D collections, and they attempt to learn 3D representations from it. The advantage in this scheme is twofold. First, 3D data of any kind, be it 3D scans, depth maps, multi-view images, or stereo captures, are all very, very difficult and expensive to collect at any reasonable quantity, and they're also near impossible to capture in the wild scenes. By contrast, acquiring 2D images is trivial. The model, and the second reason why we want to train from 2D images is that if we do so, then any model that we have will already be trained within the wild data, which means data that we acquire just walking down the street. And so it will be robust to whatever 3D reconstruction and understanding tasks we have, even when we throw it out into the wild and we remove it from a controlled lab situation. So now we have an architecture such that the discriminator operates entirely on 2D views with no 3D ground truth data required, and also such that the generator creates a single 2D view per scene, which eliminates the multi-view data requirements that many other would suppose when you're trying to create a 3D object generator. This method doesn't come without its drawbacks, though, primarily in computational cost. GAN convergence, so GAN training, can often require as many as 25 million synthesized images or more to converge. That's quite a lot. Further, this type of training often requires rendering the entire image every time we want to do it. And neural rendering, especially in a fully differentiable fashion as we do, is also very computationally expensive. Let's do a little bit of a deep dive into the underlying 3D representation so that I can give you a little bit more context for that. So for many 3D GANs, including the majority of the varieties that I'm going to be talking about today, NeRF or its variants is the representation of choice. So NeRF, short for neural radiance fields, up at the top there, is a paper that was first published in ECZV 2020, so 4 years ago, not even that old. And NeRF is a formulation for a neural volumetric representation in which an MLP learns the 5-dimensional function that maps from a position in space and an incident ray direction to a volumetric density and a specular RGB. Then to render from such a representation, it's quite simple. We can just trace rays through the space and composite the final color via volumetric ray merging. Though to do so often requires as many as 100 to 200 samples per ray. The good part about this representation is that it's trivially fully differentiable, which means that we can use it very easily in a lot of our AI methods. And additionally, this method requires only RGB color to train. There's no necessity for 3D ground truth, such as depth maps or geometry, that may be ambiguous. The bad part is that this method is, in many ways, extraordinarily expensive. To render a single image at 512 by 512 resolution with, let's say, 100 samples per pixel would require as many as 25 million forward passes of the MLP. Let's dig deeper into what that number means. So to understand why these 3D GANs could be so computationally expensive, we need to really understand this representation in context. The standard NeRF MLP consists of several stacked fully connected layers, that's the architecture on the left, that form an MLP that must be evaluated once per sample in order to render an image. Per image in order to achieve, per image in order to achieve high quality, we ideally want to render every ray, and per ray we require at least 96, but we'll round that to 100 samples per pixel to prevent undersampling the volume of introducing noise. This leads us to the aforementioned 25 billion evaluations of the MLP per image. Beyond that, recall, per GAN, we require 25 million images to converge. Combined naively, this could lead us to over 600 trillion forward and backward passes of this network that is required in order to train a single GAN model to convergence. At a glance, it becomes obvious why this is prohibitively expensive in many ways. So the good news is there's a few things that we can do to make this cheaper. Let's dissect that. For starters, the network is ginormous. If we could shrink the compute cost of evaluation, that would be a great place to start. Additionally, if there were a smart way to reduce the number of samples that we render, or sorry, the number of pixels that we render, we should grab it. Finally, we waste a lot of compute evaluating samples in space that isn't actually useful. That could be, for instance, in the case of rendering a head, the empty space in front of a person's face where there's just air, or the occluded region behind a person's face where you can't see it because it's occluded. If we were to intelligently place our samples only in the regions that we care about, for instance, right on the person's skin, that could save us a lot of compute. I'm going to wrap back around to the last one. It becomes important in a few slides, but we'll touch back on it. The last thing that I should mention here is it is in some ways potentially possible to reduce the number of images that we have per training. I'm not going to touch on this one too much. Yeah. Let's talk about the first point, though. How can we reduce the size of the network? So rather than the standard implicit MLP, which receives the input as position and code and direction, so it receives the input, position and direction and directly encodes that into a volumetric density and color, or rather than an explicit feature grid on the right, which directly looks up density and color from a predefined feature grid, we experimented with and proposed a hybrid representation which combines the two to get benefits of both worlds. So our chosen hybrid representation consists of 3 axial-aligned feature planes, which contain spatially varying information, hence why we call it a triplane representation. And we combine that with a very small MLP, this little green box at the bottom, which is actually only 2 layers, and which is designed to decode the positional information into spatial density and color. To note, we still must run this decoder equally as many times, so 600 trillion times per image in many cases, but because it's so much smaller than the original MLP, the cost of doing so is dramatically decreased. This triplane architecture also brings a good number of nice benefits to the table. First, it's easy to generalize. The stationary structure of the 2D planes makes it really easy for a model to learn and predict the content on these planes. Second, the planes are really memory efficient compared to 3D voxels and other representations because they scale only quadratically versus cubically in terms of spatial resolution. This means that we can fit a lot more spatial resolution into the same number of parameters, and that's especially important when we're trying to push photorealism on a limited compute budget. Third, 2D planes are especially compatible with existing off-the-shelf 2D backbones. For instance, we can leverage existing and well-understood StyleGAN 2 architectures to generate these 2D feature planes. Let's touch on the second point here, which is another way we can reduce the computational load of GAN training is to reduce the number of pixels that we actually render with our NeRF. So many early 3D GANs leverage 2D convolutional super resolution layers on top of a low fidelity 3D representation. We can see that here. In the middle is our low fidelity NeRF, so that's our volumetric representation with the paired geometry. And then on the left is the super resolved output. So the underlying 3D object here helps guarantee good geometric quality, and the additional convolutional layers add the missing details and ensure good image sharpness. So all while being trained to maintain consistency with the underlying 3D representation. So following the techniques that I outlined just a few minutes ago, we can train a model on entirely 2D ground truth data from which we can synthesize these photorealistic images and videos with complete disentanglement of the scene and the camera, all inferencing at real time. So there are a handful of other approaches in recent years that look to address the same issues that we addressed in different ways. For instance, rather than rendering a low resolution image and applying it through a high resolution supervision and super resolution, a possible solution is instead to render a small patch of the image at full resolution. So for instance, that is the approach taken in these two papers. On the top is Mimic 3D and on the bottom is Epigraph. So while this certainly allows higher fidelity within the receptive field of the patch, these methods can and oftentimes do struggle in terms of global consistency in the final representation. There you go, skipped one more slide. Another approach that is possible and that many other 3D GANs attempt is to bypass the expensive volumetric representation in entirety, replacing it instead with sparse representations such as multiplane images on the top or radiance manifolds on the bottom. While this approach works quite well and certainly does solve the computational complexity issue, they often need to be tailored to specific fields and can suffer a lot in terms of generalizability, whether that's diversity of objects or difficulty in representing non-frontal scenes. These sparse methods are often tailored to the specific field and often fail in these extreme cases. Let's return back to a super resolution idea though. So this, while certainly cheap and efficient, is an imperfect solution. Applying super resolution in 2D does have its downsides. Observe on the left-hand side here, the same 2D texture sticking artifacts that we saw in StyleGAN 2 in the original 2D GANs. In case you forgot, that's where for instance, the hair texture in particular will stick to the camera and cause aliasing and flickering as the object moves. So additionally, while the geometric quality in the middle and the right is quite decent and globally consistent, there is a lot of ambiguity, especially in the fine details. So, there we go. the next logical step for us was to examine how can we do better. Our goal was to maintain the extreme versatility and generalizability of these 3D volumetric representations, but still allow us to solve the fine-grained 3D detail and maintain global consistency by, instead of rendering patches or low-resolution approximations, natively scaling the resolution of the 2D images that we render. Ideally, though, without inheriting the exorbitantly high compute costs of NeRF. So what if we just try naively? There's really two fundamental problems that we face. The first is of computational complexity. If we naively scale to the same setup, if we naively scale the same setup to 512 by 512 resolution, it becomes prohibitively expensive to train. Requiring over 0.5 terabyte of VRAM in order to hold the forward and backward passes of the gradients per image. The second problem that we run into with this setup is in terms of quality. Even at the same 100 samples per pixel, we're still undersampling the volume, leading to noisy artifacts in rendering. Look on the right side, you see these salt and pepper artifacts, especially in the nose. So if we do want to actually render each pixel, we really need to find another way to make our method cheaper. Recall way back, we had 3 easy methods to reduce the training cost of our GAN. First was the size of the NeRF representation. Second was the number of pixels that we want to render. And third is the number of samples per pixel. We're going to actually go back and address how we do this third one. So rather than sampling approximately uniformly across arrays in order to find points of high density, which, as you see on the top, naively samples both the empty regions in front of the person's face and the occluded regions behind the person's face, we really wanted to sample only the interesting parts directly on the surface, for instance, you see on the bottom. So our major modifications to enable this is twofold. First, we propose a generalizable feed-forward sampler, an oracle, if you will, which tells us where the surface is located and where and what regions of space we should really be paying attention to. And second is we needed to restructure the volumetric representation away from the vanilla NeRF, instead towards a surface-aware SDF-based neural field, which would enable higher fidelity 3D geometry and be much more amenable to the efficient sampling schemes that we propose. So how does this oracle work? First, we'll take our image and we'll cast a low-resolution probe through the volume using naive sampling methods. This will inform us of a low-fidelity estimate of the volume with a scene, and then we can train a convolutional neural network to convert this low-resolution information to an intelligent high-resolution estimate of where objects are in space. We can then use this in our second pass rendering for the full resolution object, enabling us to efficiently sample only the regions of space that we truly care about, even though we're operating at previously unattainable resolutions. At the end of the day, this allows us to create precise and extraordinarily high-quality geometric details, all because we are able to render each and every pixel that we see using 3D methods instead of 2D approximations. So now that we know how to make high-quality fake people in 3D, let's get to the interesting stuff, which is how do we actually use that to make high-quality real people in 3D? So I'm just going to talk a little bit about this AI 2D to 3D lifting approach that we presented and that we submitted and presented at SIGGRAPH last year, called real-time radiance fields for single image portrait view synthesis. And this is an algorithm which, given a single RGB image, creates the 3D avatar of the person, which we can then manipulate and render as well. So our design philosophy here behind this was really to answer the question, if we have a creative use of AI, how can we make this 2D to 3D lifting as absolutely simple as possible? So what that meant is we had a few goals that we wanted to keep in mind. First, it needed to run entirely on consumer hardware, ideally in real time. The goal here was that we would have a nice, easy algorithm which wouldn't require an entire data center of compute in order to run. Second, we wanted this to use single view inputs only. For instance, a single RGB image or video feed from a common webcam that all of you have at home already. This would eliminate the need for expensive scans, complex captures, or unusual hardware that you all too often see when trying to recreate 3D from 2D. Finally, we wanted this to be a one-shot method to in-the-wild images. And what that means is regardless of which person steps up to the camera and how they look that day, whether they've gotten a new haircut or changed the way that they do their makeup, we wanted this to be able to run instantly without having to do any per-person fine-tuning or adjustment. So, an obvious place to start with this problem is GAN inversion. What is GAN inversion? So I spent the last, 30 minutes now, talking about how we could use these generators, these screen boxes on the left, to create 3D humans. And so these models implicitly understand what is a 3D human. What that means is that we can then iteratively inference these GANs in order to acquire a 3D human, which looks like the 2D target image when we render it for a certain view using a two-stage process. First, we'll use iterative refinement to find the latent code in a pre-trained GAN for a 3D human that approximately reconstructs the target image from a specific view. And then we can optionally add a lightweight fine-tuning step to the generator to make it so that it matches the exact pixel-wise identity. I'll give a little demonstration here, if this video will play here. There we go. So here's what that looks like in practice. In the first second or so of that video, we found the latent code that looks really close to our person. And in the second second or so, we use that to update the generator a tiny bit to get the exact match. At the end of the day, what we'll have is a 3D object that when we render it from the same view, will look like the input image, but is still truly 3D. There's a few key issues with this method, though. The first is that the 3D representation, in this case, the NeRF, is not necessarily easy to train from a single view. There's a lot of ambiguity that gets introduced during the rendering operation as you flatten a 3D object to a single 2D image. So unless you have a very, very carefully designed optimization scheme, the NeRF can and easily will fall apart. Additionally, and possibly the more motivationally interesting caveat here for us, is that such an iterative process is exceedingly expensive. If we were to run this on a video, the time lapse that I'm showing on this screen here is a tuning progress to match the person on the left that takes place over 20 minutes. And if we were to run this on a video, we need to repeat this every single frame, which would be extraordinarily slow and certainly would not match our real-time requirements. So in our current, in the work that I'm presenting now, which is the live portrait 3D from, in this work, we want to explore a bit of a different training paradigm and ask the question, if instead of trying to train from a limited set of 2D images, we have an infinite amount of photorealistic synthetic 3D ground truth data, can I train an efficient model to directly do this 2D to 3D lifting? Of course, just a few minutes ago, I said and I quote, 3D data is prohibitively expensive to source in quantity, so why am I proposing this? And the answer actually is kind of easy. It's because I've spent the last half hour talking about how we can train a 3D model to create infinite, cheap, accurate, and fast 3D data that we can then render out into paired photorealistic 2D images. So why don't we just go ahead and use that? To reiterate, what I'm proposing here is we're going to take an existing pre-trained 3D foundation model and use that as a synthetic data source to create an infinite supply of 3D data, and that enables us to train a separate and brand new AI model with no requirements of 3D ground truth at all. So the architecture that we really propose is this vision transformer-based feed-forward encoder, which in real time, excuse me. Such a method would operate in real time on a single GPU as fast as 16 milliseconds versus the 2.5 or more minutes for GAN inversion. What that means is that we achieve a 10,000 times speed up compared to previous methods. Additionally, our proposed method avoids squeezing the representation through any low-dimensional GAN space latent codes. And what that means is that we can preserve these person-specific and highly complex details. Additionally, our method would require no precise camera pose and is entrained entirely with synthetic data with no requirement for expensive or complex 3D ground truth. So if we look closer at the requirements of this network, though, we're going to notice that there's actually two conflicting goals with our 3D reconstruction. The first is that given a single image, 3D Lifter needs to create the canonicalized 3D representation with accurate geometry. What that means is we need to take some arbitrarily posed image and convert that to a person where we know where they're looking and how they're looking. But the other thing that needs to happen is we need to make sure that all of the high resolution details are properly copied to the right locations, despite there being no obvious correspondence between a 2D input image and an output 3D object. So to achieve this goal, we actually propose a two-step approach. First, we're going to take our image and we're going to extract some low resolution 3D deep features with a deep feature extractor, and then feed that to a vision transformer. We're going to then take these and combine these with the high resolution but globally incoherent details using a second vision transformer. And what that does is it produces a final output triplane, which is both 3D consistent, but still maintains the same high resolution details that we originally wanted. So to reemphasize, our model utilizes only strictly synthetic data that is generated on the fly during training. We found that in order to properly generalize to these in the wild images, well, we need to add some somewhat aggressive augmentation schemes to our generated data. Some examples here. For faces, we modify the pitch and the yaw of the training data on the left. We also modify some other camera parameters like the focal length or the principal point. And our model actually generates not only the RGB images, but a handful of other intermediate data points that we use during rendering, including the triplane, the depth, the rendered features, and the low and high-res images, all of which can and often are used to supervise our 2D to 3D model training. So to give a more complete idea of what happens at the training time, at each gradient step, we'll first sample a latent code. We'll then take this latent code and turn it into a triplane using a frozen existing 3D generator. We can then take that and render the triplane from two different cameras, camera 1 and camera 2. The intrinsics and extrinsics of these cameras are sampled from reasonable priors. We'll then take this triplane encoder that receives one of the images as input. And then that will predict a triplane, which will then again render from the same cameras. And then we can compare them via several losses. For instance, standard reconstruction losses or adversarial discriminator-based losses. At the end of the day, here's the results. So a few interesting and honestly really surprising things that we found is that our model shows really amazing generalization to these out-of-domain inputs. So what that means is that we can use odd expressions, strange makeup and accessories, and even despite being trained only on these photorealistic synthetic data, such a model actually transfers extremely well, even when applied to stylized and cartoonish images, as you see on the bottom. Awesome. So what we found is that despite having baked no implicit or explicit temporal memory constraints, this model still worked amazingly well on videos, simply by processing each of these frames independently and in sequence. Great. So now that we've gotten here, we can finally get to the fun stuff. We've covered what we were looking at in terms of 3D human synthesis, and also how we actually do this 3D synthesis. But I think it's finally time that we get around to why we want to do so. So the most obvious application, and the one that we have to show you here today, is a technique for 3D telepresence using AI. So why did we choose this really difficult task of lifting 3D objects from an ambiguous 2D input directly? Well, one obvious reason is that it allows us to trivially compose existing 2D modification methods, for instance, stylization.
And personalize your experience with animated avatars, stylizing them with simple text prompts. And personalize your experience.
So by applying these existing techniques to edit or stylize in 2D, we can then directly lift these to 3D, which is unlike some other methods which rely on consistent and true 3D inputs. So here's an example of how such a pipeline could work at the end of the day. First, we'll go and create a stylized 2D image. For that, you can grab your favorite text-to-image AI tool, say Stable Diffusion or DALL-E, and customize the avatar however you want. Then you need to collect a 2D video of yourself and animate the stylized image, for instance, using NVIDIA Maxine's live portrait. Finally, we can take that 2D stylized video and lift that into a 3D video in real time. Another possible edit that we could compose is the Maxine AI eye contact. This feature means that we could maintain eye contact with the viewer even if we're reading from the script or somewhere else. As you see in the middle, eye contact off, on the right, eye contact on. Additionally, while existing 3D methods wouldn't be able to do this editing in 3D, we can, because our 3D approach works entirely off of a 2D video. If we know where we're rendering the head from, we can manipulate the eye gaze in the 2D video such that it maintains eye contact even after we render it into 3D. A few other couple of fun things that we can do. We can rewrite our input images using existing 2D algorithms, which may enhance the sense of realism as we transfer people from their homes into shared world spaces. Or we can completely change identities, even in a photorealistic manner. Obviously, for this one, if you apply it in a malicious fashion, then there's a few concerns about deepfakes and the likes. So take this slide with a grain of salt. One of the more interesting applications, though, is consistent real-time translations. While it's really not difficult to dub over existing video methods, doing so suffers from obvious desynchronization between the audio and the video. So by composing a multi-step pipeline of translation, then reanimating the face with the new audio, in 2D, then lifting that 2D reanimated face to 3D, we can eliminate the desynchronization and still achieve accurate 3D reconstruction despite having no 3D ground truth. And all of this utilizes existing well-understood 2D methods. And all this that I presented here today isn't just speculation or thought experiments. As Ken introduced at the beginning, we actually showed an early prototype of this pipeline at the SIGGRAPH Emerging Technologies last year. And earlier this year, just a few weeks ago, we had an upgraded version in a booth at NVIDIA's GTC conference, where we incorporated a handful of upgrades and extensions, including XR headsets, higher resolution models, and cloud microservices. Before I wrap up and open up for any questions, I'm sure there's going to be a good number, I want to take a moment to thank all of my incredible collaborators. Without each and every one of these wonderful individuals on the screen, I'm really sure I wouldn't be here to be able to present all of this really fun stuff with all of you. So thank you, and thank each of you for stopping by. I think, so that's it. I will open up for questions now.
What you're doing is very interesting. And can you talk more about how you plan to apply this, the applications? Because I remember in your opening, you mentioned that you would get around to why you're doing this. And I'm very application oriented. So I'm just curious, how does this get used in practice?
Absolutely. Yeah. So a lot of the stuff that we've been looking at recently is, for instance, right now I'm on a Zoom call. You're on a Zoom call. I can't see you. You can barely see me as a tiny little couple of pixels in the corner of your screen, probably. It's not a great experience. It's acceptable, but if there were 4 people talking, you don't know who I'm talking to, what's going on, right? It's a little bit strange. But if instead you have 4 people, for instance, sitting around a conference table, and I am going to look to my left and talk to someone here, you know, like if you're looking at my camera, I'm now talking to someone else, right? Or maybe I'll talk to someone else over here, right? I don't know if you can see that in my camera, but it's just, there's a lot of social cues that we lose as we move to these little pixels on the screen calls where everyone's looking at everyone and no one at the same time. That's one of the things. And also there's just been a lot of studies recently on that, perhaps because of this lack of social cues, these Zoom calls and Teams calls are really mentally fatiguing. We just wanted to see, like, using these methods, if we can improve 3D teleconferencing by making a 3D object and a 3D people that you see on your screen. Maybe it's a more fun or a more engaging or just a more enjoyable experience.
Right on. So this would be like a metaverse, whether you're watching it on a screen or a VR headset, it would be like a 3-dimensional room, conference room that you're creating? Mm-hmm.
Yeah, so you'd have, for instance, instead of people on little tiles, you'd have people sitting around a conference table and you can look at each other and communicate. And yeah, that's a way to put it for sure.
Very cool. So if you're looking at one person or another, I guess you're tracking my gaze or my head motion when I'm looking at different people on the screen, and then my avatar is replicating that.
Yeah, for sure. That's a way we could do it.
Cool.
Thank you.
But, you know, Ed, there's also, if you would prefer to have your very cool self sitting there as opposed to the person who did not want to wash their hair that morning, you know, you could always be looking good. Anyway, we have
show up in your suit and your fancy, you know.
Exact.
Yeah, even though you're in your pajamas and yeah.
Hey, we have Audrey coming in. I don't want to talk over here.
Yes.
I especially like the idea of being able to put in a substitute when I haven't washed my hair. That's perfect. But also, I am always interested. You go through all these efforts to create, you know, 3D mesh and 3D objects. I would love to be able to, in some way, download them and take them into other packages and things like that and use them. With the animation, of course, attached to them would be even a bigger bonus.
Mhm.
How do you envision that happening in the future?
It's ongoing work. And the reason why I say that is because at the moment, as I mentioned, we're using this volumetric NeRF representation, which is, it's really, it's not an ideal representation. It's easy to train, it's easy to learn, but it's very expensive, and it's honestly, it's kind of like low fidelity. You've basically just got a cloud in the shape of a person.
Right.
Mm.
And you never turn that cloud in any way into a 3D mesh.
No, we don't. Some methods do. So for instance, Metaverse, the pixel codec avatars from Meta, uses an actual animatable mesh, and they transmit codes that animate that mesh instead. And it looks really good, but that requires that you create your mesh, which is difficult and expensive. But we don't, and it's definitely ongoing work. We're doing a lot of work on that. But I agree, if we could take these objects that we've created from these 2D images and just use that and, I don't know, drop it into a Unreal or drop it into somewhere else, that would be great.
It would be amazing. It would be wonderful.
Yes.
So thank you for this wonderful presentation. I really loved it. Thank you.
Thank you.
Yeah, thank you so much for the really nice work. Yeah, I just wonder, like, have you encountered any like temporal artifacts when you generate those talking like videos when the person moves or talking? If so, have you applied any like temporal regularization method or consistent loss to make sure the texture looks natural? Yeah.
You all have such good questions. The answer is, in these slides, no, but as of about 3 months ago, yes. So it's also ongoing work. It's a paper that I recently submitted that does more temporal fusion of frames and people as they evolve. So for instance, if I'm looking to my right here, you see this side of my face, and the current model just kind of forgets what's going on at the back of my head, so it will hallucinate it. And we'll come up with some reasonable guess. But for instance, if I have face paint on and I turn my head, it forgets that I had face paint on. So it will just like erase the face paint until I turn back and the camera can see it again. We don't want that to happen. So we have, I have a paper recently, I don't believe it's public yet, that addresses this problem.
Cool.
But at the moment, no, but ongoing work, definitely, yes. We want to have that.
I have a question. It's not quite related to the neural nets and everything, but it's the appearance of the eyes and whether they're tracking you or not. And you look at the 3D models and they're recessed in. Why is that happening? And is that, is that an accidental thing where you get the eye tracking with that?
Yeah.
The old sculptures used to have that, I think, right?
Yes, exactly. Yeah, so it is an artifact of the training data set. So if you look way back at these old sculptures, actually it's a slightly different reason. The reason why the old sculptures have these holes in their eyes is because people used to put gemstones there, and then the gemstones got stolen. So there's nothing in the eyes now. Ours is a slightly different reason, which is that most people, when you take a picture of them, look at the camera. Just because, people like looking at cameras, smiling at the camera. And what that leads to is that most people, regardless of where you're taking the picture from, have their eyes looking at the camera. But when you're trying to create a 3D model of a person that doesn't change no matter where you look at it, you also still want to mirror that artifact of the people looking at the camera. And the way that that manifests is not by the eyeballs moving as you change the camera, because then obviously the 3D model is moving and that would be bad. So it instead uses optical illusions, which, for instance, if you're familiar with the term the hollow face illusion, it's where you have a concave object instead of a convex object. And the way that that works is it looks like the eyes are tracking you when they're concave as you move left and right, even though the eyes are still, just because because of the optical illusion, essentially. So
Thank
to
you.
recap, it's an optical illusion that is a result of a data set bias. Whereas if we train on cats, which don't tend to look at cameras for whatever reasons, cats don't like cameras, we don't get the same artifact. Cool. That's also you all have, like as I mentioned, really great questions.
Actually, I do have a question.
Please, yes.
If this is used for video teleconferencing, what is the bandwidth requirement?
That's a good question. So rather than streaming the renderings of the person in and out, we're actually streaming the full 3D representation. So it's these triplanes. And for those of you that are familiar with this machine learning, the triplanes are a tensor of shape. Sorry, it's a set of 3 tensors, each of which is shape 256 by 256 by 32 channels. And what that basically means is that we have a 2D image that has 32 colors, and we just take it, we organize that into a big tile, and then stream that with video compression. So nothing fancy really under the hood. We just shove it through a normal video encoder, and that ends up being about 10 megabits per second up and down, which is honestly not that much more than a normal video call. Like it's quite manageable. I imagine if 3 or 4 more people turned on their cameras here, we'd be able to match 10 megabits per second up and down.
How do compression artifacts manifest themselves in this model?
Yeah. Because we're doing this untiling and retiling of the 3D object and then compressing it with 2D video codecs that are optimized for human perceptual vision and not for whatever 3D representation parameterization that we're streaming, there are visible, in many cases, compression artifacts. We do a lot of work to reduce those as much we can on the training side. But when they do manifest, a lot of the time it's small flickerings, for instance, smoothness and inconsistency, especially for instance, like hair textures or super fine details. Details sometimes get very slightly smoothed out, or slight inaccuracies in like color shift. So for instance, the light might turn a tiny bit red for a frame and then turn a tiny bit blue for a frame and then go back to normal for a while. They're small, noticeable if you're really looking for them and know exactly what you're looking for, but for the most part, they don't cause too many problems.
Thank you.
I see a new hand just came up. Go for it.
Is there a portal where you can input your own images and play around, or
There
and
is
any
not.
any thought of having one? And also, is there, you can put any hook points where you can hook your own functions in this processing chain?
So for data privacy reasons, we don't have that right now. Just a matter of data privacy at the moment. I'm not sure if we will ever get around to doing that, or in the near future, we hope to productize this, and perhaps it might show up like in your somewhere else. Do we need beta testers? Not at the moment, but maybe we will soon, but not at the moment. But we don't have any way to publicly access this right now. In short.
Okay, thank you.
Thank you.
I was just wondering what happens if you run a person through like the cat model or vice versa?
That is a really good question. A lot of the time it doesn't work very well. Because the cat model is trained on cats and the person model is trained on people. The first thing that's going to fail is the landmark detectors. where when you're trying to look for a person in an image, if you only see a dog, then it's gonna not find a person. But if we really do our best to like force an image of a dog through the person model or a person through the cat model, it's really strange. You come out with like a cat-shaped object, but with human eyes and human teeth, and it's just uncanny.
Don't happen to have any examples here.
I don't happen to have any examples, but you'll just have to believe me that it is extraordinarily creepy.
All right, thank you.
I see a few questions in the chat. The first is, do you have any links? The answer is yes, and I will get that to you, but in a moment. The second question that I see here is, what's the expected latency of the encoded triplane representation to decoder to 2D rendering for the purpose of video conferencing streaming? So the end-to-end latency is about 80 to 100 milliseconds. Between when I capture, between when the photon leaves your face, arrives to the camera, and then exits the display on the other person's end. So we can budget that to about 10 milliseconds of 10 to 15 milliseconds, depending on which model we're doing of, actually, no, I'll back up even more. We'll budget that to 0 milliseconds to capture an image, 5 milliseconds to track your face, about 15 milliseconds to stream it to a server, another about 15 milliseconds to convert that 2D image to a 3D object, another about 20 milliseconds to stream that back to the client, and then about 20 to 30 milliseconds to actually render that image out. Sorry, render the 3D object back out to an image that the receiver can see. End-to-end, as I mentioned, about 80 to 100 milliseconds. That is on par with existing 2D video conferencing systems. So this Zoom call, I know how to see it on Teams, but I don't know how to see it on Zoom. Probably has about 100 to 200 milliseconds of latency as well. So yeah, thank you for the question, Hasharma. Any other questions?
There was a question by Audrey there in the chat also. Do you need beta testers?
Yeah, we do not at the moment. Thank you for the offer, but we do not.
I would love,
Thank you,
ahead.
June.
I would love to read the paper that you talked about. This is Audrey.
Yes, I have several papers. Let me go ahead, and now it seems like a good time to actually minimize this stuff. And
You gave us a lot to take in, which was great. And now I just want to review it and read it, think about the whole thing.
there
So
will be plenty.
And we can post them in the YouTube and Meetup afterwards too, if you don't have them handy. Or
I do have them on hand.
I think people can save the chat also.
Yes, let's see if I can stick this into the right chat to everyone. So on that page, I'm not actually sure why I'm missing some papers, but on that page from bottom up is efficient geometry aware 3D generative adversarial networks is the first 3D generative model. Yeah, I'm missing some papers. Live portrait 3D, or live 3D portrait is the second, not second, that's the third one. So that's the 2D to 3D converter. That's probably the paper that you're interested in. And then what you see is what you GAN. NVIDIA, rendering every pixel, here we go. This is the second. And that's the second model that I introduced, which is the high quality 3D generator. And that is I believe, the three main papers that I covered here today.
I have a question, Ed
Please.
here again. This is cool stuff. I have an application where in fact, I'm writing specs for merging a real world immersive stage live performance stage show, like in a dome.
Okay.
Right, where the dome imagery on the dome comes onto the stage, you put live performers in there, and they're interacting with the immersive environment projected around them.
Okay.
And I want to lift those performers off the stage and put them into metaverse as digital twins, right?
Okay. Yeah.
Like how far are we from full body capture and digital twin creation kind of a thing, do you think?
Ongoing work. I'm working on a project right now for at the moment, as you may have noticed, we only do faces and a little bit of the upper shoulders, but mostly just faces. Turns out that heads are relatively easy because, with the exception of mostly the mouth, they don't really move around that much. But when you have a whole body that has a skeleton and you can wave your arms and your hand and you can occlude your head and do weird stuff, it becomes a little bit more challenging. So
Indeed.
a lot of questions there, but we are working on it, and I'm not sure I can give you a nice estimate, but I hope within the next small single digit number of years.
Yeah. Yeah, that's cool. You know, I mean, obviously we can have mocap trackers on the
Yes,
performers,
of course.
which can be a little cumbersome and you know, in terms of costuming and everything.
Mhm.
Another way of doing it is real-time volumetric with clusters of cameras all around.
Yes.
You know, and I've seen that in real time with, like, I think it was like a 3-second latency that Canon did of a real-time basketball game. You can
Yeah,
put
I've
on a
seen it
headset,
sports
right?
games. Uh-huh.
It was very cool. You can walk right out onto the basketball court, and the players are running through you and everything.
They look really good.
Anyway, I just thought I'd ask that. It's
Yeah. Yeah.
We have had some prior speakers, and you can check out our old videos of various ways of motion capture.
Cool. Thanks.
Michael, is there one thing that you didn't cover that you wanted to and you didn't think you could fit it in? Or one more little tidbit?
There's a few. I think future directions would be interesting, but actually that came out a lot in questions, which is future directions of, can we make it look better over time? Can we make it learn from you as a person? So for instance, you know, you go home and you see your brother or your sister, your family, and you know what they look like because you've seen them so many times every day. Can we make an AI do that so that it can just be you when you're, somewhere else? It can pretend to be you in the boring calls that you don't want to join. Or at least maybe not like pretend to be you, but when you're in your pajamas, it can make you look like you when you were not in your pajamas. Or questions like, can we do hands and body? Right, a lot of future work, things that are really interesting, really exciting, that are coming up soon, we hope.
All right, well, we hope you're going to be at SIGGRAPH.
Yeah. I hope so too.
Did you submit something to SIGGRAPH this year, or is there which conference are you submit?
I didn't submit anything to SIGGRAPH this year, mostly because I was crunching for NVIDIA's GTC. Same deadlines. SIGGRAPH was like a few weeks after the GTC conference, the
Oh.
submission. So
Yeah, that's
I
cool.
just didn't have the available waking hours to attempt that.
We will
But
find you.
yes. But you know, it is how it is. I might still attend. We'll see.
Actually, I have a question. So
Please.
can I like train like the 3D model like on a younger version of myself, and then like you look younger in the video call?
So can you ask it for a younger version of yourself?
But if I maybe show it a picture, and then it'll select the real me in the video call, and then use the younger version of myself to make the 3D image from like will that actually
Yeah.
work?
Yeah, so the great part about our method here is that you can just take your 2D image of you, feed it to a 2D age, you know, reverser, whatever 2D model you want, spits out a younger image of you, and then you just turn that into the 3D you. Yeah. There's nothing stopping you. Yeah, it should be quite easy to do. Should be a piece of cake.
Are you concerned about the next level of deep fakes then?
Am I concerned
terms
about
of-
deep fakes?
Well, I mean, yes, impersonating people more with that.
Yeah. The short answer is yes. The long answer is we're doing our best to be responsible about this. Again, part of the reason why we don't have a public version right now is because if you have a 2D image of a person, it's like, it might be a deep fake, but if you have a 3D video of a person, that becomes a lot more convincing. So we're doing our best to be responsible and make sure that nobody can make deep fakes of it. But as with any technology which takes a human and turns that into another human, there's gonna be some bad actors. The short answer, yes, I am concerned. And yes, I am thinking about it.
Really amazing work. Very impressive.
Thank you so much, Matthew.
Thank you.
Presentation.
Thank you. Yeah. Thanks everyone
Great stuff.
for attending.
Yeah, thank you very much. So if there's no more questions, maybe we'll bring the meeting to an end.
Yeah. Thank you, Les, for inviting us all in to witness Matthew in, action.
Thank you all.
Thank
That was a
you.
great talk. Thanks a lot.
Fingers crossed. Here we go.
Thank you, SIGGRAPH, for doing this too. Thank you.
Yes, thank you.
Cheers.
Bye, everyone.
Cheers, everyone.
Bye.
Okay. Bye.